In this video, we're going to see the last question of the 2015 HSC exam. It's the last part of the last question. So, it's complex numbers and it starts with, let n be a positive integer. By considering cos alpha plus I sine alpha to the power of 2n, show that cos of 2n alpha equals this expansion here. So let's go ahead and attempt this question. Okay, so part I, it says to consider cos alpha plus I sine alpha to the power of 2n. Now, let's get back what the question is asking us to prove. We have a cos 2n alpha here, so this is going to probably suggest to us that somehow we're going to use de Moivre's theorem, because we can see that the power has been brought down into the angle. And on the right hand side, well, what do I have? I have cos to the power 2n alpha. I have all these binomial coefficient terms, so that means I'm probably going to use the binomial theorem for this part. So first of all, let's do the easy part, which is de Moivre's theorem. So this is equal to cos of 2n alpha plus I sine of 2n alpha. Fairly simple, and let's call that equation number 1. And I should probably say by de Moivre's theorem. Great. Now let's have a look at expanding this in terms of a binomial expansion. Now this is going to get quite long, so what I'm going to do, I'm going to say let C equal cos alpha and IS be equal to I sine alpha, simply for the sake of simplicity. Just so I don't have, it's going to be messy using C and IS, but with the cos alpha and I sine alpha, it's just going to be long and messy. So I'm expanding C plus IS, but now I'm expanding it using binomial expansions. So the first term, hopefully you're very confident with binomial expansions, is going to be 2n choose 0, C to the power 2n, IS to the power 0. We don't need to write it. The next term is going to be 2n choose 1, C to the power 2n minus 1, IS to the power of 1. The next term, we're going to write a few of these out. 2n to the power 2, C to the 2n minus 2, IS squared. The next term, 2n choose 3, C to the power 2n minus 3, IS to the power 3. The next term, 2n choose 4, C to the power 2n minus 4, IS to the power 4. Now here I'm going to stop writing terms because you can see that here I've stopped at 2n to the power 4 before I have my dots and then completing off the expansion. So plus some dots, and now let's see where they started up again. We have a 2n choose 2n minus 2, so let's get one of these terms in. It's going to be 2n choose 2n minus 2, C to the power 2n minus 2n minus 2, so really that's going to leave me with a squared, C squared, so I don't need that n. And then here I have IS actually, to the power 2n minus 2. The next term will be 2n choose 2n minus 1, C to the power 1, IS to the power 2n minus 1. And my final term is going to be 2n choose 2n, C to the power 0, so I don't need to write that, IS to the power 2n. Alright, so you can see this is quite long here. Now what I'm going to do, I'm going to look for all these IS's. Now we need to remember that I stays as I, obviously. I squared is negative 1, I cubed is negative I, and I to the 4 is positive 1. And we're going to use these facts here, where we have i's. So 2n choose 0 is just 1, so I can leave as it is and just have c to the power 2n times 1. Now this term is I. I'm going to write that out the front. 2n, choose 1, c to the 2n minus 1 s to the power of 1. Now here I have I squared times s squared. So this I squared is going to be negative 1, and I have minus 2n, choose 2, c to the 2n minus 2 s squared. Here I have I cubed, which is negative 1. So that's going to be is negative I, so that's minus I, 2n, choose 3, c to the power of 2n minus 3 s cubed. Here I'll have I to the 4, which is 1, so that is 2n, choose 4, c to the 2n minus 4 s to the 4. And now I have dots again, all the way up to, starting up again. Now here, what do I have? I have I to the power of 2n minus 2. That's the same as saying I to the power of 2 times by n minus 1. And then that is the same as saying negative 1 to the power of n minus 1. So the I to the power 2n minus 2 here becomes negative 1 to the power n minus 1, multiplied by the binomial coefficient 2n, choose 2n minus 2, c squared, s to the power 2n minus 2. This term here, well, what's that going to be? That's going to be negative I to the power, negative I times negative 1 to the power of n minus 1, 2n, choose 2n minus 1, c squared, c to the power 1, so just c, and then 2n minus 1. And then my final term, well, what's that going to be? That will be plus 2n, choose 2n is simply 1. Now I have I to the power of 2n, which is the same as I squared to the power of n, which is the same as negative 1 to the power of n. So I have negative 1 to the power n, s to the 2n. Again, because this binomial coefficient is 1. Now I'm going to realize that in my question, I only have the even terms. Let's move it down. The even terms. So this was 2n, choose 0, 2n, choose 2, 2n, choose 4. And if I look here, all my even terms are real. C to the power 2n is real. This term here is real. It has 2. The next even term is 4, which is real. And every even term is going to be real. And every odd term is going to be imaginary. So I am going to equate from 1, I'm going to equate the real part here, which is cos 2n alpha, which is what I want, with the real parts in this expression, which is going to be precisely what I needed. So this is equation 2. So I'm going to equate real parts of 1 and 2. And in doing so, I will get cos 2n alpha equals c to the power 2n. Now I'm going to rewrite these as cos and sine, but the only reason I'm doing that is because now I want to get this, which is going to be nice to have it in the same form as the question. So this is going to be cos to the power 2n alpha. This is imaginary. The next real part is 2n, choose 2, cos to the 2n minus 2 alpha, sine squared alpha. The next real part, 2n, choose 4, cos to the power 2n minus 4 alpha, sine to the 4 alpha. I just fit that on the page. Okay, and then plus up to, now this is another real part, so this will be negative 1 to the power n minus 1, 2n, choose 2n minus 2, cos squared alpha, sine to the 2n minus 2 alpha, which was that term, and then the final term is going to be from here. So plus negative 1 to the n, sine to the 2n alpha, and you will see that this is exactly what I needed to prove in part I. Now, part 2. what does part 2 ask us? Part 2 says, let t sub 2nx equal cos of 2n cos inverse x for x between -1 and 1. And it asks us to show that t of 2nx, so in other words, this thing, is equal to this. Now, when I look at this expression here, I can see that it's almost identical to this, except the only difference is that alpha, oh, you can't see, the only difference is that alpha now has been replaced by cos inverse of x. So, what I'm going to do is I'm going to substitute cos inverse of x into this equation for alpha. Now, one thing that we should also notice, here I had coses and sines. Here I have x powers of x, and I have powers, it seems, of 1 minus x squared. Now that's interesting because what do we know about sine squared and cos squared? Well, we know that they're related by cos squared plus sine squared equals 1. So wherever I see a sine squared, I'm going to make that 1 minus cos squared. Okay, now that we have that in mind, firstly I'm going to again use these c squareds and s squareds and so on, just for simplicity. So cos 2n alpha, let's move that up, cos 2n alpha, that's cos, so c 2n, minus 2n choose 2, cos, so c 2n minus 2. Now sine, I'm going to write that as 1 minus cos, so 1 minus c squared. And then here I have 2n choose 4, c to the 2n minus 4, and sine to the 4, well that's sine squared all squared, so that's 1 minus cos squared all squared. So that's going to be 1 minus c squared squared, plus some dots, -1 to the n minus 1, 2n choose 2n minus 2, cos squared is c squared. Now for this, what do I have? I have sine squared to the power of n minus 1. So that's going to be 1 minus cos squared to the power of n minus 1. That's a minus. And the final term is -1 to the power n, sine squared to the power n, so 1 minus cos squared to the power n, 1 minus c squared to the n. Now I'm going to go ahead and substitute in, wherever I have an alpha, I'm going to substitute cos inverse of x, because once again, that's what I'm looking for. I'm looking for t to n of x, which is that. So substituting that in gives me cos of 2n cos inverse x. Well, I'm going to get cos of cos inverse x to the power of 2n. What's that equal to? That's simply equal to x to the power of 2n. Now, I'm going to write it out just so that people can see it and not be confused with what I'm doing. Cos inverse x, and that's raised to the power of 2n. Here I have 2n choose 2, cos to the 2n minus 2 of cos inverse x, multiplied by 1 minus cos, am I going to fit it in? Yep, I'll fit it. Cos inverse x. Okay, now I've written enough terms here. I think we can see the pattern going on. So plus all the way up to, now this term, I can just write the final term, -1 to the n, 1 minus cos squared of cos inverse x to the power n. The final step is to realize that everywhere that I have cos of cos inverse x, that's just going to become x. And so I'm going to get x to the 2n minus 2n choose 2. This is x to the 2n minus 2. And here I have 1 minus x squared. 1 minus x squared. And then if I had the next term written out, it would be 2n choose 4. X to the 2n minus 4 multiplied by 1 minus x squared. And this thing here is squared. And so now, all the way up to and including -1 to the power n, 1 minus x squared, and that will be to the power of n. And that is all we needed to show for that part. Okay? Now let's have a look at part 3. By considering the roots of t to nx, find the value of cos pi on 4n times cos 3 pi on 4n, multiplying all the way up to cos of 4n minus 1 pi divided by 4n. Okay, so what do I have? Part 3. It says to consider the roots of this expression, but what does that mean? That means I'm setting it equal to 0. But what is t of 2nx? That is simply, as given in the question, t to nx is cos 2n cos inverse x. So I'm really solving cos of 2n cos inverse x, solving that equal to 0. Alright. Now I'm going to see where is cos equal to 0. Well, hopefully you know that. It's going to be pi on 2 plus integer multiples of pi, but if you can't see it, we'll then just draw a diagram, a very rough one. This is pi on 2, this is 3 pi on 2, this is 5 pi on 2, and so on. Each time I'm adding pi onto pi on 2. So therefore, the argument of cos, what's inside of cos, is equal to pi on 2 plus k pi. Okay, let's do a bit of rearranging. I can factor out pi and make a common denominator, and I have 1 plus 2k on 2. And now I'm going to divide by 2n and get cos inverse of x is equal to, now let me write this as 2k plus 1 times pi divided by, and I'll have 4n in the denominator. Okay, so that means that x is going to be cos of 2k plus 1 pi divided by n. Now, what are the values that k can take? Well, let's think about this. I'm solving this thing equal to 0. So what I've just found, I've found the roots of this thing, which are x equal to this expression for different values of k. But how many values of k should I have? Well, that's going to come from here. I'm solving this equal to 0, which is really solving this polynomial equal to 0. This expression here is really a polynomial. Now, the fundamental theorem of algebra tells us that a polynomial of degree 2n, and the highest degree here is 2n, so this is a polynomial of degree 2n. That means we're going to have 2n solutions. So, taking that away, that means that I should start from k equal to 0, 1, 2, 3, all the way up to, now if I want 2n solutions, I've started at 0, so I go all the way up to 2n minus 1. And these are going to give me, once I sub in these values of k, they're going to give me all the roots of this equation, which is really solving a polynomial equal to 0. It's going to give me all of these roots. Alright, now let's get back what we're looking for. We're looking for a product of all these cos functions. So, let's just write out a few of these solutions. When k is equal to 0, I'm going to have, I should write a 4 there, I should have cos of, that'll be 1 pi on 4n. I'll also have, for k equals 1, I'll have 3 pi on 4n. And then I'm going to have cos of 5 pi on 4n. And I think we can see the pattern all the way up to, now if I sub in 2n minus 1, I'll have 4n minus 1. So cos of 4n minus 1 times pi divided by 4n. And you can see that these look remarkably similar to what we have here. We have a product here. So I have a polynomial, which is really this expression here. This is my polynomial. I'm solving that equal to 0, and I know what the roots are. So I can use my product of roots formula, which says that the product of roots, taken one at a time, are equal to the coefficient of x to the power 0, which is really the constant term, divided by the coefficient of x to the highest power. I'm going to say that that's going to be p, and I'm going to say p is the degree of the polynomial. of the polynomial. Okay, now I'm missing something here. What I really also need is -1 to the power of p. Now you can see this because when we have a quadratic equation, it's c on a, right? We're familiar with that. When we have a cubic, it's going to be -d on a. And every time it's odd, there's a negative out here. Every time it's even, there's no negative. So to take that into the general case, we make it -1 to the power p. All right, so now that we have that, what is the coefficient of x to the 0 in this polynomial up here? Well, firstly, our product of roots is going to be -1 to the power of p, where p is the degree of the polynomial. That means the highest power of x. And we've already said that the highest power of x in this expression, in this polynomial, was going to be 2n. We'd get a 2n from here, we'll get 1 from here. In fact, we'll get it from every term. So there's going to be -1 to the power 2n. Now, what's the coefficient of x to the 0? Well, where do we get x to the 0 from? In other words, where do we get the constant term from? Now here, clearly there's no constant term. Here I have something x multiplied by something, so when I'm going to get something that's related to x no matter what I multiply. Here is the same case, and the only place that I'm going to get a constant term is going to be from this last expression here. Because if I expand this binomial expansion out, my first term is going to be 1, and then it will be minus 2n, n choose 1 x squared. But the only term really that's going to give me a constant term is going to be here. And the constant term from this expression, you couldn't see that, from this expression here, is going to be -1 to the n. So the coefficient is -1 to the n. Now I'm going to divide that by the coefficient of the highest power of x, which is 2 to the n. And I'm going to write x to the power 2n. And we're going to work this out separately now. So the coefficient of x to the power 2n is equal to what? Well, let's have a look again here. From here I have x to the power 2n. Well, the coefficient is clearly 1. Now what about from this term here? Well, I'll get x to the power 2n when I multiply this x, which is by itself, with the last one here. You'll see that x to the power 2n minus 2 multiplied by x squared will give me x to the 2n. So the coefficient will be -2n on 2 times -1. So it's going to be positive 2n choose 2. And here I'm going to get x to the 2n from what? I'm going to get it from multiplying this with x to the 4. Where do I get x to the 4 from? That comes from the last term in this expansion, which again this is going to be positive, and I'm multiplying by something that's positive. So I'm multiplying 2n choose 4 by positive 1, so that's going to be 2n choose 4. And this pattern is going to continue on all the way up to the last term. What is the power of x to the 2n here? Well, that's going to be 2n choose 2n. Okay, now this is right, but we need to kind of simplify this a little bit. So, in order to evaluate, we need to consider a certain binomial expansion. Consider the following. Consider 1 plus x to the power 2n. Now what's that equal to? That's just a simple binomial expansion. Simple, I mean simple relative to the rest of this question. 2n choose 0 plus 2n choose 1 times x plus 2n choose 2 times x squared. I'm going to write a few of these out so we can see it. X cubed, 2n choose 4, x to the 4, and all the way up to 2n choose 2n minus 1, x to the 2n minus 1, and the last one is going to be 2n choose 2n, x to the 2n. Now, what do I see? Here I can see that I have every even binomial term. I have 2n choose 0, which is 1, 2n choose 2, 2n choose 4, and these are all the even ones, so every second one. So somehow I want to eliminate the odd ones. And the way to do that, well, firstly, let's also say that I have x's here and I want to get rid of the x's. So I'm going to really substitute x equal to 1 in. So I'm going to say let x equal 1. Here I'll have, well, 1 plus 1 is 2, so I'll have 2 to the 2n. That's going to be equal to 2n choose 0 plus 2n choose 1 plus 2n choose 2, and we can see the pattern all the way up to 2n choose 2n. Now, as I was saying, I want to get rid of the odd terms, so what I'm going to do here, I'm going to let x equal negative 1. In doing that, this will become 0. Now, all the even terms will stay positive, but all the odd terms will be negative, because negative 1 to the power of, to an odd integer power, is going to be clearly negative. So this is really now negative 2n choose 1. This is positive 2n choose 2. The next one would be negative 2n choose 3. And then I get up to, well, 2n is guaranteed to be even, so this is going to be positive 2n choose 2n. So I will call this equation 1, I'll call this equation 2, and I'm going to add them once I get some paper. Alright, adding these two together, 1 plus 2. Now, on the left-hand side, I'm adding 2 to the power 2n to 0, so that just stays as 2 to the power 2n. And when I add these up, I'll get 2 lots of all the even ones, and the odd ones are going to cancel with each other. So I'm going to be left with 2 times all of these even binomial coefficients. That'll be 2n choose 4, and all the way up to 2n choose 2n. So, dividing by 2, that'll give me 2 to the power of 2n minus 1 is equal to, this thing here is 1, and these stay as they are. The final term is also 1, but I'm just going to write it as 2n choose 2n. And now you'll see that this is my coefficient of x to the 2n. It's this expression. So therefore, I can say that the coefficient of x to the 2n is equal to 2 to the power 2n minus 1. And so therefore, I can now substitute that back into this, which is my product of roots. So I can say that my product of roots, and that's a symbol for product, I'm sure you should know that, product of roots is equal to negative 1 to the 2n. Now this is always positive, this is always even, so that means that this is always going to be positive 1, no matter the value of n, times by negative 1 to the n, divided by the coefficient of x to the 2n, which is 2 to the power of 2n minus 1. But what are my roots that I'm multiplying? They are precisely these values of cos here. So that's going to be cos of, let's see, pi divided by 4n multiplied by cos of 3 pi divided by 4n multiplied all the way up to, let's write cos first, cos of 4n minus 1 pi divided by 4n. And these are equal to, well, we said that this was always going to be 1, so it's going to be negative 1 to the 2n divided by 2 to the power of 2n minus 1. And that answers this question, because now I've found the value of this expression here. Now, for the final parts, IV, it says, prove that 1 minus 2n choose 2 plus 2n choose 4 minus 2n choose 6 all the way up to negative 1 to the power n times 2n choose 2 is equal to 2n cos of n pi over 2. So, let's write down what I'm required to prove. Part 4. I'm required to prove that 1 minus 2n choose 2 plus 2n choose 4 minus 2n choose 6, and it's good to note that there's an alternation going on here, all the way up to negative 1 to the n, 2n choose 2n equals 2n cos of n pi on 2. Now, I have an alternation, but I have an alternation in the pi's. sorry, not in the pi's, in the even terms. So I only have even terms, but I also have an alternation. So how can I get that alternation in the even terms? That's the question here. Okay, now there are a few ways I think that you can do this, but my favorite way is to go back to this expression here. We considered the expansion, the binomial expansion of 1 plus x to the power 2n. Now if I do that, 1 plus, let me just write it again so we have it in front of us. That was equal to 2n choose 0 plus 2n choose 1x plus 2n choose 2x squared plus 2n choose 3 x cubed. I'm going to write up to 4, 2n choose 4 x to the 4 plus, and the last term was 2n choose 2n x to the 2n. Okay, now if I let, see, I'm writing what I'm speaking. If I let x equal to I, what do I get? I get 1 plus I to the power of 2n is equal to, this is 2n choose 0 plus 2n choose 1 times I plus 2n choose 2 times I squared plus 2n choose 3 times I cubed plus 2n choose 4 times I to the 4 plus all the way up to 2n choose 2n, 2n choose 2n, that's messy, x to the, not x, I to the 2n. Okay, now I'm going to once again use my knowledge of I and write these in a certain way. So this is going to be I times 2n choose 1. This is going to be not plus, but minus, because I squared is minus 1, so minus 2n choose 2. This is going to be minus I, 2n choose 3. Now I to the 4 is positive 1, so I have plus 2n choose 4. What else do I have? I have all the way up to, this is 2n choose 2n, but what's I to the power of 2n? Well, that's I to the power, I squared to the power of n. I squared is negative 1, and so I have negative 1 to the power of n. Now, let's keep in mind what we want to prove. Okay, so I've got this. Now, what is the the left-hand side equal to? Well, 1 plus I, hopefully you can, I'm assuming, I mean, if you can follow along here, you should be able to convert this to mod arg form. That would be root 2 of cos pi on 4 plus I sine pi on 4. And I raise that to the power of 2n. So that's equal to, I'm just going to say that that's the left-hand side. Left-hand side equals. Now, if I use de Moivre's theorem here, this is going to be, well, root 2 to the half to the power of 2n. So that's going to be 2 to the power of n. Cos, now de Moivre's theorem, that gives me 2n pi divided by 4, so n pi divided by 4, plus I sine n pi, sorry, this should be a 2, n pi divided by 2. And now I can see that I have 2n times cos 2n divided by 2, and what I want to prove is 2n times cos n pi divided by 2. So what I'm going to do, I'm going to equate the real part on the left-hand side with the real part in the imaginary side, and we can see that that's going to be 2n choose 0, which is 1, minus 2n choose 2, plus 2n choose 4. If I had some more terms, it would be minus 2n choose 6, all the way up to negative 1 to the n, 2n choose 2n, and I will have completed this question. So let's write that down. Equating real parts from left-hand side and right-hand side. and that gives me my answer. 2n cos n pi on 2 equals, where am I? Equating them here will be 2n choose 0, which is 1, minus 2n choose 2, plus 2n choose 4. The next term would be minus 2n choose 6. The next one would be 2n choose 8, but I'm not going to write that, all the way up to negative 1 to the power n, 2n choose 2n. And that is the final question of the 2015 HSC Extension 2 exam. Hope you enjoyed it.